OctConv Convolution, and just to as a preparation, let's look at the convolution operation. So this is the input feature maps to a convolution layers. These come in height, width, channel, and of course it's usually a 4-dimension tensor. You have the batch, usually denoted N, then the channel, then height and width, and so forth. But let's discuss one instance because it's gonna just be replicated across the entire batch. Okay. A normal convolution layer is defined by the kernels acting on the convolution and these on the input representation and the number of kernels. So a certain kernel would be, let's say, 3 by 3. So it would be 3 by 3, and its width, its depth depends on C. So this C, this number input channels, it depends on, so it's the same C. And a convolution would take this filter and sweep it, yeah. So it will pad with zeros and place it on each pixel, the center on each pixel of the input feature maps, and wherever it like for example for this pixel, each corresponding weight, each position multiplied by the part of the filter that is placed on, and all summed. This all gives me 1 pixel of the output. So sweeping like this, since I sweep the entire feature map, input feature map, it will give me just 1 channel of the output, assuming we're padding and we're not skipping. So it will give me H and W and just 1 channel. If I want, let's say this is C in, if I want C out of them, so I want C out feature maps, then I will need C out of different convolution filters. So the convolution filter is Cn, K by K. So it's K by K. Oops. So it's K by K by Cn. And the number of the convolution filters determines how many channels of the output, because each one will just give me 1 slice. Okay. So in the paper they say the convolution operation. So at the PQ pixel, so this, let's say this dimensions P and Q, P in height and Q in P in y-axis and Q in x-axis. So this entire P and Q is gonna be P and Q and C out, right? Let's not care about C out because it just depends on how many filters you have. But P and Q itself for each slice is determined by what? Is determined by, well, the convolution filter of that specific slice. So let's say the first outer slice here, being positioned in PQ of the input and doing the multiplication. So the multiplication is what? Well, it's just revolving around each index of the spatial part of the filter and vector dot product this vector with the part of input that of this vector in the weights with dot product with this vector in the input and so forth. So basically it is pi pq is equal for all the neighborhood in this region. So we're gonna sum over all the pixels, all the span of k by k. So I and j depend on neighborhood of size k, this neighborhood. Each picking out so it's going to span from minus k minus 1 over 2 to k minus 1 over 2. The minus 1 is this odd part. So here 3 by 3, 3 minus 1 is 2.5. So minus 1, 0, plus 1. Yeah. So here would be I minus k minus 1 over 2. Sorry, plus. Yeah. Comma. J plus k minus 1 over 2. So y plus, because when I is minus k minus 1 over 2 plus k1 minus 1 over 2, you get 0, which is, so assuming the count will go from 0 to k from the I dimension. So these are k plus 1. X at point P plus I Q plus J. All right. Yeah. So this dot product would give us 1. Yeah. And then we repeat for all the possible vectors in the filter. And this is what this sum gives us. Right. So assuming, so the expenses come here. How many flops here? Flops, which is floating point operations. Well, every time we place the filter, there's going to be what? K times Cn, right? Multiplications. K times Cn multiplications, right? And the same amount summation, right? We're gonna sum them all together. Yeah. Times however many pixels we have, H times W, right? times however many filters we want to give out, C out. So these are the flops. So what they're proposing, what they're proposing in the OctConv operator is to, so these H and W, instead of, so these H and W, instead of having and doing all the convolution over them, let's say we do it alpha percent, like 50%, alpha percent with the original H and W, and 1 minus alpha percent with half their sizes. Okay, so you end up with 2 still k square cn, well, not all cn, sorry, yeah. Here they say the cn is going to be already factorized by your input is going to be factored twice. Some part of it is the real H and W, and the other would be H over 2, W over 2. So your input would be discounted Cn alpha H W, and out of the C out also would be C out alpha. Okay, so this is one part. Next part would be can I go down, please? Next part would be plus 2 k square Cn 1 minus alpha H over 2 W over 2 C out 1 minus alpha. Okay, so this is this part producing producing the low dimensions part, and then the inner play. So this is the output as well. So this producing this is this. This producing this is this. The interplay, this producing also to this, and this producing also to this. So what they do is technically is you're supposed to upsample this first, so it goes back to the original distribution, original spatial dimensions, and then apply convolution. But instead they would say, okay, well, apply the convolution here and then upsample. Okay, so you end up with a convolution 2 k square Cn 1 minus alpha, right? H over 2, W over 2, C out, but this time is it's alpha, right? and then you upsample. Let's assume that the upsampling it's a nearest neighbor upsample. Let's assume, it doesn't take flops essentially. And for this, it says do average pooling first, and then apply a convolution, which is 2k squared cn alpha. These are the number of channels. Which is going to be h over 2. We do average pooling first. C out 1 minus alpha. And the average pooling would be for each pixel in the output. So average pooling would be summarizing, for each pixel in the output, there would be one operation between four adjacent pixels. This is gonna be 0.25 this plus 0.25 this plus 0.25 this plus 0.25 this. So this is gonna be h times w, h over 2 times w over 2. This will give me the number of pixels here, and applied times cn times, per equation we have how many? One, two, three, four, plus it's 4 plus 3. So end up with 7 over 4 cn hw. Yep. Let's see. Here they folded the feature map as follows. So we said the high is gonna get the high is gonna get information from the high and from the low. From the high, it's a regular convolution. From the low, well, instead of upsampling, like we said instead of upsampling, regular traversal, if you go this far, if you travel this much in regular dimensions, when you're squished like this, you travel this much, right? So a movement of the filter that goes like this is going to be divided by 2 to pick up the information. So here it says, well, you can pick it up from the low dimensional one, just shorten your step, basically divide your step by 2. Yeah. The opposite is true when you go from high to low. From high to low, you're here in the high, and you want the filter to get information. A small movement here in the low is going to be like double the step here, right? So if you, when you move on to the next element when in the short and the squish dimension, that means you jump twice here. So this is the same, like twice the jump. Yeah. However, since the index of x high can only be an integer, we could either round to the next the index 2 times p plus I, or approximate the value at 2 times c plus 0.5 plus I by averaging all 4 adjacent locations. The first one is also known as triad convolution, and the second one as average pooling. As we discussed in section 3.3 and figure 5, convolution leads to misalignment. We therefore use average pooling to approximate this value for the rest of the paper. An interesting and useful property of octave convolution is the larger receptive field for the low frequency feature maps. Convolving low frequency part XL with K by K convolution results in an effective enlargement of the receptive field by a factor of 2 compared to vanilla convolutions. This further helps each OctConv layer capture more contextual information from distant locations. Implementation details. As discussed in previous subsection, what is this half again? We're multiplying by a factor of 2 to the location. Yeah, performs the downsampling and further shifting the location by half a step to ensure downsampled maps will align with the input. No. For the interfrequency communication, we can again fold the downsampling of the feature tensor XH into convolution as well. We're multiplying a factor of 2 to the locations. PQ performs downsampling and further shifting the location by half step is to ensure downsampled maps will align with the input. Instead of routing it to 2 times p plus I, 2 times q plus j, conduct convolution with stride 2 for downsampling, we adopt average pooling to get more accurate approximation. This helps alleviate misalignments that appear when aggregating information from different scales, as shown in Appendix A and Appendix C. A, it just says, strided convolution. C, epidation study, okay. We can now rewrite the output y into a high and low parts of octave convolution using average pooling for downsampling as regular convolution over the high part from the high to high, regular convolution for on the low part for the low to low. But when it comes to low to high, high to low, they do average pooling on the high, then convolution, average pooling on the high, then convolution from high to low. This is bad because information here is supposed to be high density, information here is supposed to be high frequency, right? You forced it to be small, low frequency. Not that it not that it's maybe not suitable to be downsampled, because if it's downsamplable, it should have been in XL altogether from the beginning, right? But you're taking high frequency, downsample it first, then apply a convolution on it. That's not good. And YH is supposed to house high frequency, right? But how come applying a convolution on low frequency and then upsampling? So this is definitely ensuring, so this is low frequency, definitely, because it came after upsample. Yeah. So why? Yeah, this makes no sense. I understand that now the convolution is, both the convolutions are happening in the low dimensional scale. So both convolutions are happening in the lower dimension, the half dimension scale. But this is definitely doesn't make much sense. However, if I were to design how do I make a new? Yeah, sure. The high, so convolution x high, w high to high. However, the second part would be convolution x low, w low to high, and then reshape. Okay, so this part is gonna be 1 minus alpha C out, right? And this is alpha C out, which is YL. So this is the dimensions. Right. And here, so the dimension is happening in the low scale, but the output is times 4. The output of the convolution is 1 minus alpha C out times 4, and do reshape. Okay, and this is, so the output here is 1 minus alpha C out. And here, X low from X low. Here the output is alpha C out, right? The number of filters, the number of filters here. The number of filters plus F X high, comma, high to low, and number of filters here is alpha C out over 4 and reshape it. Let's see. K square Cn C out 1 minus alpha squared HW. So X is 1 minus alpha Cn alpha Cl XL. So H, yeah, Cn C out 1 minus alpha squared HW plus this part is K squared Cn C out alpha squared. So this part H over 2 W over 2 plus this part is K squared. Who is acting? So the number of input is alpha Cn. Cn C out alpha 1 minus alpha, and the dimension is H over 2 W over 2 plus K squared Cn C out alpha 1 minus alpha, oh wait, times 4 times 4 plus H W over 4, right? So this cancels these. Let's say it's 50-50, okay? So we end up with K squared Cn C out So this is 1/4 here, 1/4 here, right? And HW times 1, 2, 2.5. Oh, sorry, not 1/2. So that's 50/50. That's 25 times 0.25. Otherwise, it would have been KCN, C out, HW, right? So this is 0.5 and 1.25, so it's 0.625, right? Yeah, so 0.625 savings. Point 625, so yeah, around almost half the number from, no, half number of flops. So this is my design. In their design, what's their calculation came out to be? Computational cost. Yeah, it's there. It's this. So if I put 50/50, 2 minus half. Let's see. So there's is a bit more economical. Yeah. So let's see. So this is 1 minus alpha squared, right? Plus alpha squared over 4 plus 1/4 alpha 1 minus alpha. Five over. Let's see. There's 0.75. 2 minus 0.75. 0.296. Okay. Uh, 0.25 times 0.25 plus 0.75 times 0.75 times 0.25 plus 125 times 0.75 times 0.25. Mine is still a bit large. But still, it makes more sense. Mine makes more sense because it still treats the high. I haven't seen there. Okay, let's continue reading. Maybe they address that problem. So they get their best results when, yeah. Top 1 accuracy. Hmm. The details of the OctConvolution operator implementation are shown in Figure 2. It consists of 4 computation paths that correspond with the 4 terms in equation 4. 2 green paths and correspond to information updating for high and low frequency feature maps, and 2 red paths facilitate information exchange between the 2 octaves. Group and depth-wise convolution. The octave convolution can also be adopted to other popular variant in the convolution, such as group and depth-wise convolution. For the group convolution case, we simply set all 4 convolution operations that appear inside the design of the OctConv to group convolutions. Similarly, for depth-wise convolution case, the convolution operation are depth-wise, and therefore the information exchange paths are eliminated. Giving only 2 depth-wise convolution. Why? We note that both group OctConv and depth-wise OctConv reduce to their respective vanilla versions if we do not compress the low frequency part. Why would that happen? Efficiency analysis. Table 1 shows theoretical application at cost, memory consumption. I guess there's not much more information left. Okay. Yeah, I guess the paper is almost done. Looking at the figures, okay. The more you compress, the fewer flops you do, but accuracy starts to falter. Well, not much. This work we address the problem of reducing spatial redundancy that widely exists in vanilla models. Was a novel octave convolution operation that to store and process low and high frequency features. Okay. Okay. I guess, yeah, it's worth using, although it makes no sense to upsample. Yeah, I don't know. Okay.